Okay, welcome to Calculus 2, right? Everyone's in the right place. My name's Robert Di Giovanni. I'll be the instructor. I recognize a few of you from previous classes. The way this is going to work, I'm going to have this little get up here, all right? I'm going to record every single lecture. So what you see on the screen is what's recorded with my audio, and then that will be put onto a website where you can look at it, watch it later if you want to. I know some of you have already visited the ACES website and probably are already aware of what I'm talking about, but I know some of you haven't. So let me show you to start off where you can get to the syllabus in case you don't know this already. You go to log into ACES, you log in. Wow, it's actually working today. Oh. Okay, has everyone seen this before? Yes? Where do you go from here if you want to get to your class? My courses. And then make sure you're in the right semester. Cal 2. So I believe this became available to you like back on like the 21st or something like that. I think is when I first opened this up for everyone. What you see here is, first of all, the syllabus. Right in the middle of the page is the syllabus. We're going to go through that real quick. The schedule, that's something that you can print out so you have it, hold in your hand, and you could also write your homework assignments on there. Our recorded class lectures, like I said, I'm recording this right now. Later on today, after class, I'll go to my office, I'll upload it to the server. Usually takes a couple of hours for the server to re-render it, but by the end of today, it should be out there, and then you can watch it and whatever. Then we have, I did this last spring, so I have my entire library of every video I did in my spring semester out there. And I actually went back and relabeled all the videos. So you can, if you click on this, it'll show all my spring Cal 2 videos with topics. Like, so you can see, like, the first one is I went over the syllabus. The next one, I talked about areas, under curves, and summations. Then I did Riemann sums. So if you get to a point in this class where we're like covering something, and even though you have the lecture I do here video, if you want to go watch another one, there's another one, because maybe I did different examples in that one than I did in class here. Okay, so you have like an enormous amount of information available to you for this class. These videos, though, I did these, well, I think these, well, I don't know, you'll just have to check them out. I'm pretty sure I did these with using the same screen capture. Let me see. I'm just going to open one up. Let's just see so we can see what the quality of this is. Ah, yeah. See, when I first started doing this, I was actually sitting there with a big old camera in the middle of the room and having to follow myself with the camera with the little remote control. It was a pain in the ass. So instead, I've got this nice system here now where it's just going to record. Let me get to something. Oh, wow. Did this freeze up on me? Now, let me get to something later in the semester is when I picked up this laptop. It's buffering. Yeah, see, so that's what it'll look like. So it's a much cleaner, and I think hopefully you'll like it. Keep in mind, I can keep track of this stuff. So like when I put a video out there, I can go and see how many people watched it. I can look at the IP address of who hit it and how long they watched it. And I'm not requiring you to do so. But if you're struggling in the class and you're like, man, I just don't know. And I'm like, I go back and, nobody has watched this video. I might ask you, why didn't you go watch any of the lectures, right? I mean, it's all here for you. All right, so that's the old one, the Cal 2 ones. And then I decided to throw out there my Cal 1 videos from this summer, just in case there's something in Cal 1 that you forgot, or maybe you never saw L'Hopital's rule. How many of you never saw L'Hopital's rule? Have no idea what I'm talking about, L'Hopital's rule. So everyone saw L'Hopital's rule? Ah, fantastic. Well, let's just say you didn't. You could go back and watch my L'Hopital rule. And then if you've never used Canvas, which is this whole blue screen thing, if you've never used it, then I have a little video there for you to watch. It just shows you some cool things like if right now, if you check your email, you have to go in here to get it. But if you set Canvas up properly, you can get it to like text you, or it can send it to your Hotmail account or something, so you don't have to constantly be coming into ACES to check your email. But you have to configure that, and that's what that little video does. It kind of helps you get started with that. Okay, any questions on the middle? We're still have to talk about syllabus and stuff, but right now I've tried it myself and it has never worked. These videos are huge, okay? Like an average video that I do in class here will probably be close to 200 meg. So that's a long time to download 200 meg, depending on where you are, right? Yeah, so and your connection. But I believe when you click on, there is a download link, but I don't know if it'll actually do it. Now, if you're interested in getting the videos, if you bring me an external drive and come to my office hours, I'll dump everything onto your external drive. I mean, like terabytes. You probably need like terabytes on that. Yeah. Okay. Now, the other things. We have a discussion board over here. It's kind of cut off. I apologize. But there's a discussion board. This isn't required. It's just if you want to go talk to your classmates, this is where you can click on this. Right now, we have no discussions in here. But, hey, it's there. Okay? You can ask each other questions. You can email me for help. Like if you ever email me for help on a problem, a lot of times I'll either write it down on this and then like send the file to you, or send you a link to a video. If you go and repost that on discussion board, that's kind of nice for your classmates, you know. Grades, when the time comes, and this, if you've had me before, I'm doing grades different this semester. The grades will be done through here. So when you click on that, it'll just bring you up, okay? It's not going to bring the whole class up. And it'll have all your grades for all your quizzes and anything else, right? And so you'll have kind of a real time, where am I in the class? And that's very helpful also for exams. I believe we have an exam the day before the drop date. So what will happen is I'll give you that exam, I'll go home, grade it that night, I'll post your grade, you'll know where you stand in the class, and then you can decide if you need to drop, okay? That sort of thing. It's good. You don't have to wait the whole weekend to see how you're doing. Questions on that? I do plan on dropping a couple of quizzes. Don't know yet how many. People, that's just a way to link to other people in the class. Files, this is important. Okay, even though there's all those videos and everything else there, if you click on files, I have multiple folders over here. It's a bit overwhelming, but first of all, formula sheets. You are allowed to have formula sheets on every exam you take in here, but you can only have this one. Okay, so if you click on that, that's it. You open that up at home, you print it off, that's what you're allowed to have. Unless I say you can also have this. You can't come in on the test day and be like, hey, I have this from an old class. It's my favorite. I sleep with it. You know, this is it. Okay, this is it. So that way there's fairness. Everyone's got the same tools. Okay, there's your formula sheets. Old class notes. So remember I said I put the videos up there for my Cal 1? Everything I write down on here, on my screen, not only is it video recorded, I can save it as a PDF. And then I send that out so that you can not only watch the video, you can have a copy of the notes that I do. So these are all my notes from my summer Cal 1 class. These are all my notes from my old Cal 2 class. And then our class notes, that's going to be this semester. So I'll start putting ours in there. Still with me? Is this like information overload, too much stuff? Okay. What I like about the notes is you know, if you bring up some of the notes, like let me see here. Unfortunately, these aren't sorted by topic, but you can figure out what they are by looking at the video. Let me see what this one was. Here we go. So, convergence tests. You know, so to me it's nice to have, even if you're sitting there with a laptop open while you're trying to do your homework, you know, you'll be able to reference this stuff. Look at how I worked examples. Okay? Close that. What else? Solutions. Solutions. I've already worked most of the problems in this book. So there's a solution manual that you can buy that has just odd problems. And then there's an instructor solution manual that has even and odd. But that book is just too tedious for me. It just looks too, ugh. So I've just worked most of these myself. So here's 6-3, partial fractions, the even problems. And it may not be every even problem, but it's at least the ones that I might assign. So there's my work. Okay, so I mean, basically you have the answers to most of the homework problems. The question is, can you do it, check your answer with mine, make sense out of it, and learn, right? I'm not holding anything back from you as far as information. The only time you're going to have to prove it is on a quiz or a test. That's when you prove to me that you understand. With me? Okay. Last thing is the schedule. So I'm going to go back to the home page. If I am ever here in class and I say, hey, I'm going to put up a review or something, I'm going to send out a review to everyone about the next exam, and I tell you I'm going to put it in the files, that's where I'm talking about. So you're just going to have to go hunt it down. I've been known before to give a take-home quiz and then put the solutions to it in there and not tell anyone. And then like 2 people come in and to turn in the quiz the next class. They're like, he had the answers on the website. Like the answer was out there. So what I want you to do is just get used to coming here and looking for things and using this resource. I think that's it. Let's talk about the syllabus. I don't like going to a syllabus and reading it because everyone can read. We're required to not hand out a syllabus now. So we're getting away from paper and all that stuff. So everything syllabus-wise is on this website. Y'all too close? That's tough to see? Because what we can do is, when class starts, what we can do is get you to, we'll kind of migrate the tables back a little bit or something, okay? I want everyone to be able to see. I'm going to say, for the most part, you're going to read this. And a week from today, I will pass out a thing that you sign that says, I understand the requirements of this course. I've read the syllabus. And that'll be our contract, okay? So you go through this on your own, but let me point out the highlights. First of all, I introduce myself. Here's the office, Juniper Hall, that's across the moat, lake-ish thing. Over there, Juniper Hall, first floor, okay? Buried in like the basement bowels of the building is my office. And I did that intentionally so people couldn't find me, except for the students. I just didn't want the administrators, I didn't want them to find me. So I buried myself in there. It's hard to get to that floor because in Juniper Hall, you can't get to the first floor from the second floor. You have to go out the building, down, and back in, which I think was an engineering error, but they say it was designed that way for cost effectiveness. I don't buy it. Someone forgot the stairwell. Okay, so here's my cell phone number. I forgot to put on here, yeah, that's my cell phone, okay? I forgot to put on here that you can text me. Just don't forget, if you text me, tell me who you are. Okay, so don't text me, hey, I'm not going to make it to class today, because I'll have no idea who you are, what class you're in. I have 7 classes. 4 of them are face-to-face, 3 are internet. So I need to know who you are if you're going to text. You can also contact me if you need help, okay? I actually enjoy math. Like, I like it. So when a student asks me for help, I like that, because that's what I do for a living. And Cal 2 is one of the classes that I enjoy doing. I can't say anything else because I'm recording this, but how I feel about some of the other classes I teach. This brings me joy. Let's do some Cal 2. That's fun to me. So I want you to be able to reach out to me and ask for help. So take advantage of it. And my office hours are another example of that. We're required to be in our office for a certain amount of time. Those are the dates and times I'll be there. Fortunately, I think for you, hopefully this works into your life. Immediately after this class, I walk back to my office and I'm there for a little bit over 2 hours. Okay. If that doesn't work for you, on Monday, Wednesday, I've got some hours there. And then on Friday, I'll be here from 9:30 to 12. Now, Fridays, sometimes we have meetings that come up. And I'll be on campus, but I won't be sitting in my office. So I always say on Fridays, just check with me before. What I'd like to see is on Fridays, because not a lot of people have class on Friday, is, a group of students that get to know each other. You form a group, and you always just come to my office on Fridays. You sit in front of my office. There's like a big round table. You just sit there and you work together. And when you have questions, you ask me. So hopefully you'll take advantage of that. Materials. I don't have a copy of the book, but if you took Cal 1 here, it's the second one. Can I borrow yours? Thank you. This is it right here. Not a huge fan of the book, but it's all right. I like the author. Just there's some other books that he writes that have a little more meat on the bones. That one works, so it's still calculus. Okay, a graphing calculator is allowed. I don't have any restrictions on calculators. I know there's some instructors that are like, you can't use the TI-89 or you can't use the TI-92 or the ones that can do all this stuff, basically. I don't have a restriction, but you always have to show your work. I mean, you always have to show all your steps and everything else in between. You can't just give me an answer. So I encourage you to use your calculator if you have it. Anybody not have a graphing calculator? No? You don't have access to one? No graphing? Okay. No go? If you can try and get your hands on a graphing one without paying a lot of money, if you have a friend that might have one, or if maybe someone in here has an extra one that they want to rent you, or I don't know, work something out. Craigslist. My calculator, yeah, my TI-89, I'm on my fourth one because I've lost them, and I think I've got them off Craigslist every single time after I lost the first one. I think I paid like $40 for this one. So I would find a graphing calculator. If you're going to do a lot of math, my opinion, as if you're going to do a lot of math, the TI-89 is the machine to get, because it does algebraic manipulation, right? It can factor, it can integrate, it can differentiate, it can take derivatives, it can do all that stuff symbolically. So anything below the 89, like the 86, the 84, they're good, but they don't, I mean, if you're standing, you've got money in your hands and you're going to do a lot of math, this is where you go, right here. Okay? I think I saw one for $35 at a what are those called? Pawn shop on Craigslist the other day. So, any questions on the calculator? You will have to graph, so you're gonna need some tool, whether it be a website or something else. You'll need to be able to graph. So this class description, you should have passed Cal 1 with a C to be here. Sometimes people get through the cracks somehow and get in here. That's the requirement to be in here. There's also English and reading requirements, but we won't talk about that. Objectives, critical thinking, blah, blah, blah. Outcomes, blah, blah, blah. Well, this is not really kind of blah, blah, blah. I shouldn't say that. I've been teaching here for a long time, and when I first started teaching here, I was... Hold on. Hold that thought. All right, back to where I was. So this concept here, the fact that we will get to this Taylor-Maclaurin series, all this stuff, polar coordinates, we will get to that this semester, all right? Who will be here to see it is a different question. I'm being honest. It's up to you. How you do in this class is going to be determined by how much effort you put into this class. I mean, you may have been a Cal 1 machine, and this class might bring you to your knees, all right? Because it's exponentially more work, all right? So be prepared for it. Standard grading scale, A, B, C, D, F. Here's the breakdown. Expect a quiz any point in time. I'm not real big on quizzes because they take up too much damn time, and we don't have time to be sitting around twiddling thumbs in this class. I have to throw as much material as I possibly can at you and show you as much as I can in the time allowed. So we can't take 20 minutes every class for a quiz, but I'm still going to let 15% of your grade be quizzes. So I've got to give them to you somehow, so they'll probably be take-home quizzes. And I may leave class today and say, hey, check your email. I'm going to send you a quiz. I may not even hand it out to you. So, but I'll always let you know, okay? I won't ever just put a quiz out there and not tell you and then be like, turn in your quiz, the one I threw out there. You didn't see it? Okay. I won't do that to you. Exams, we will have 3 exams in class. That's the plan. If we fall behind, I will take one of those exams and make them take home so that we can gain the class day back. You don't want that. You want an in-class exam, okay? You definitely want an in-class exam. Take-home exams are not easy, all right? A lot of people think they are, like, yes, I get to take home. They usually require about 16 to 20 hours to finish a take-home exam. So let's try and avoid that. Let's stay on track. You do your part, I'll do my part. We stay on track. We'll have in-class exams. I mean, how much can I ask you in an hour and 40 minutes, right? But if I give it take-home, well. Final exam, 25%. Attendance policy. Well, this is a college level course. We're in Cal 2, so at this time you probably know you should probably come to class. But the fact that I record these things sometimes lends people to feel like, okay, well, you know what? I can always watch the recording and I'll be all right. That's why I do it. Because if you do miss for like you got sick or, I don't want you to fall out of this class because of one day you were absent. But if it becomes this thing where you're really just taking advantage of the fact that I'm recording, then, you can be withdrawn from the class or I can fail you at the end. So keep that in mind. Even if you have straight A's on everything and you exceed the allowed number of absences, which is 4, then at that point I can drop you, even if you're hundreds on everything. So please communicate with me. If you're missing days, let me know. Hey, I missed today because I had a doctor's appointment, or I missed today because I needed sleep, so I didn't come to class. I'll watch the video later. Whatever it is, just let me know. Electronic devices. So I don't allow for you to have your cell phones or iPods or anything like that out, because I don't know what you're doing. So just keep these away for the hour and 40 minutes that we're in class. Disconnect yourself. You're off the grid, okay? No Facebook updates, okay? There are penalties for that. So if I see you and you're kind of like under the table like this, I'll, trying to do 10 points off your next exam. So it's not worth it. If you're expecting, of course, an important phone call or something's happening, just let me know before class. We're all human. Life happens. Behavior. Sleeping is the big thing. So you sleep, I ask you to leave. 10 points off next exam. So if you're real tired, you're not going to be able to hang in there, it's better to take the absence and watch the video later than to come in here and get 10 points off. You know what I'm saying? I'd rather you sleep in the hallway out there for an hour and 40 minutes drooling all over yourself than to be in here doing it. Scholastic dishonesty, cheating. It's pretty simple. You cheat, you're given an F in the class, and that's it. I don't really usually have a middle, like this area of okay, here's your slap on the wrist type. It's just usually you cheat, hey, nope, bye, F. So we won't go there, right? Tutoring. Cal 2 tutoring. Well, you can go to Juniper Hall 316. There are some tutors in there that can help you with Cal 2. Just be careful, because it's very difficult to be tutored by someone who's taking Cal 2, and it's difficult for someone who just took Cal 2 to tutor Cal 2. So I would be looking in the tutoring lab for anyone who has a degree in math that can tutor you. All right, so you'll find them. There's one tutor in there that I know for sure by name. Her name's Daniela. Has anyone ever met Daniela? Okay, she's a mathematical machine, so she can help you with Cal 2. Now, she just got exposed to sequences and series, so she might not be able to help with that, but it wouldn't be surprise me if she already figured that out. So, all right, 6 drop rule. You get 6 drops your entire academic career. This is state legislative stuff. I'll let you read that. SOBI, strategies for behavioral intervention. Basically, look, if you see someone in class or in the hallway or just around campus that just looks like they're off, like they're about to just completely go off and start going on a shooting rampage or something like that, just people like just seem like a little bit weird to you, just report it, talk to someone about it. And if there is an active shooter in the building, down the hallway, Where are we going? Yeah, probably. Let me see what's there. I haven't checked this room yet. Well, let's see what we're looking at here. Yeah, there's nothing to break our fall. It's gonna hurt. You're gonna limp away and you're gonna be in a cast for a while. But the alternative, yeah, it's concrete. No, there's some grass out there. Anyway, but look, it's if we are faced with that, we'll be somewhat prepared. We at least know that is a way out. Okay. All right. That's the schedule. I'm not going to. I'll bring up the other one. This one I had to put in here. It's real ugly, but I'll bring out the one that you can print. The rest of it's all stuff I have to have in there. I can't take out. All right, there's your syllabus. Here's the schedule. Let's see what this looks like. Like I said, I would recommend just go home and print this out, bring it, put it in a binder or something. I give all my homework assignments in class. So one of the things that happens a lot of times is that a student will miss class, and then they'll email me and say, what did I miss? What do you think I'm going to tell them? Go watch the video, right? Before you come ask me what we did or what homework you have, go see what you missed first, because it'll be in there in the video, all right? And a lot of times when I send you the file that has the notes, I write the homework assignment in there. So you could just look through it and be, oh, here's where you put the homework problems. So the homework will be given in class. I do that because I don't really know how we're going to do every day. I don't know how far we're going to get into a section, so there's no sense in me locking us into something if we don't cover it. So right now, don't know. Those are the sections, though, we do plan on covering. So we're going to start with 4, 7, 5, 1, 5, 2. We'll kind of go in order through the book. We'll have a review. This day we'll actually have the lecture, then we'll do a little review, and then the next day we have exams. So we don't have that first exam, we're not going to have a full day of a review. It's just going to be partial. And then we continue 6-1 because we're not going to complete it in this day. We're going to do the first half of it. And then we'll continue on Chapter 6, take an exam on Chapter 6. We'll go into Chapter 8. Like I said, this was that chapter that was missing for a long time. And then look at 8. 8 is easily 2/3 of this class. I mean, not 2/3, sorry. Easily a third or more. And then we get into Chapter 9. And then your final. Now, I think I accidentally put us here on Thanksgiving, right? November 28th? Isn't that Thanksgiving? Isn't that Thanksgiving? So I'm sorry, but cancel your plans with your family. No. I'm going to have to fix that. I did that for my other class too. So, oops. This is a tentative schedule. It may change depending on how things go. All right. That's the schedule. I don't think there's anything else here for me to talk about. Do you have any questions? Oh, attendance. Hey, this is new. This is how we're going to take attendance. Let's see how this works out. Does everyone feel like they're sitting in a place that they'd probably be okay for the rest of the semester like this? No? How can we rearrange? Which way? Well, then they'll have their backs to it. You mean everyone across? What do y'all think? I don't care how you sit. I want you to sit in the way that you'll feel best. Do you want to do straight rows or do you want to do groups? Do you care?
Put 2 sets of tables here, or I can 3 sets and pull one of those back.
Yeah, we need to get this table moved more into the center. Can we move? You can't really go back much further, can you? How about we connect? I don't know if that'll fit. I don't know. Why don't you're back as far as you can go, right? Pretty much. Why don't you take that table all the way to the back and you sit, instead of sitting on the end, sit like that? Take it all the way to the table. Okay, and then you, same thing now. We want to leave a little bit of a space to get out in case we need to. Do you think y'all can put it here? Just slide that table right here? I think you still might be a little too close, but yeah. You want to go straight across with it? Whatever you think. The thing is, it's going to get changed by every class that comes in here. They're all going to change everything around. Just to keep that one on, yeah. That seem like it'll be a little better? Just watch your bag, guys, right here. I don't want you to get anything rolled over in there that was important. That better? We'll see how this works. Okay, so what I'll do is I'm going to do attendance this way today. I'm just going to call names. So, Mohammed, Ian, Jacob, Robert, Demas. If I mess this up, I'm sorry. How do you say it? Demas? Cameron, you're here. Daniel, Garrett, Elias is here. Joseph, Gonzalez. Yes? Jose, Colin, Claudia, Joseph, Luke, Chance, Sarah, Jaime? Jaime? Oh, man. Okay. It's going to take me a while. Sorry. Catherine, Miguel, Norby, Zachary, Christopher, Michael, Franklin, Aurora. Wait, Aura. Aura? That's right. You look familiar. Were you in one of my classes a long time ago? No? Okay. Abdul? And Joshua. Damn, 100% attendance. That's pretty good. All right. Now, I don't want to do that every day. Okay, this is a calculus class. You don't come to class, I mean, that's kind of more on you. But just know that probably I'll do a sign-in sheet that'll go around every day. And then I'll come back later and fill this in. Two tardies. So if you come in late, what I do is I mark it, not like you're absent, but I'll mark it as a late instead. 2 tardies is an absence in this class. Tardy to me is like anything over like 15 minutes. I'm not saying come to class 10 minutes late every day. I'm just saying like if it's habitual, we're going to have a problem. But I don't want to lock myself into a certain time. Okay, 5 minutes, you're tardy. All right. Check this out. Trust me, we're going to get started, but check this out. So I was telling you I can kind of take a look at everything. So these are the analytics for our website. Give it a second to load. There we go. So I can bring up students right now, and I hope I don't embarrass anyone. I'm not trying to. But the blue bar here indicates how many pages that student has looked at on Canvas so far. So I can already tell if someone has even been here or not yet. What is this over here? Oh, attendance. So I've taken attendance there. I'm not saying if you haven't been here, I'm already upset with you. I'm just saying that I can keep track. If like a week from now you still haven't been here, you'd probably have to explain why that is. I'm ready to start. No questions? Okay, here we go. Here's the way I'll try to set up every day. You walk in, you sit down. I don't know if I'm going to stay here or not. This is a kind of a weird position. I want to be like up on a lectern, but they don't have lecterns here. So I may move somewhere else, and I can actually go wireless with this also and like move somewhere else in the room if I need to. But for now, for today, this is where I'll be. I'll come in here. I'll put like what today is going to be and then what we're going to be doing for next time. So right now, we covered the syllabus, attendance, seating, we've got that. I'm going to do an introduction and then talk about areas. And then we're going to go for next time. That is your homework assignment. Now, I don't collect homework, okay? I'm not going to take homework up. It's not part of your grade. It's only quizzes and exams. But hopefully you learned in Calculus 1 that you should do not only the homework assigned to you, but the homework in the book that's close to the problem that was assigned to you. So if the instructor assigns number 5, you should probably do number 6 too, just to get more, practice. Is everyone okay with the idea that you have to do the homework? I'm not going to check it. It's on you. So that's your homework for next class. Quiz, next time. We will have a quiz. Not going to tell you what it's over, but it's going to be a quiz. Yes?
So that's the homework that we do tonight.
That's right. For next time, that homework is due. Okay. Yep. So this will be due next time. I mean, when I say due next time, I mean it should be done. You should understand that problem, and you should, at the beginning of class, ask me any questions on that problem if you have any. Mm-hmm.
I have the calculus book, I think it's SAC.
Okay.
Can I use that book?
Well, the homework problems won't match. Is it a completely different author?
Yeah.
Yeah, you're in a situation. The library has the book, so you can get the homework out of there. Anyone else in that situation where they took it at SAC or another school and they have their book? You have the same situation? So that's it, just 2 people? 3? They're similar enough that you could probably get by. Yeah, you'd have to check, though. You'd have to maybe check with your partner across from you and be like, hey, let me compare mine to yours, the homework assignment. But they're the same in sections and stuff, what they cover. Yeah. Some of the problems, yeah, they changed up some of the problems, and then so that's why you could get in trouble. If I assign number 5, but it's really number 3 for you, it could be an issue. Yeah, so maybe you can sell it back or something. I don't know. Okay, quiz next time, and next time we will cover 5247. Okay, that's the plan. Now, before I get into the whole concept of areas, I wanted to actually start by talking about what Calculus 2, what we're going to be doing in here, all right? Just kind of a quick introduction. And maybe the best thing to do to start would be to talk about what Cal 1 was about. What was Calculus 1 about? Okay, derivatives. The derivative idea came from the concept of the limit, right? So we actually started with the limit. From the limit, we developed the concept of the derivative. Does anybody remember the definition of the limit of the derivative? The limit definition of the derivative. It's the limit. H approaches 0. That's right. That's correct. That is the limit definition of the derivative. So in Cal 1, you started with the idea of the limit. Then we introduced the idea of the slope of the tangent line. And we're able to come up with this formula for it, this equation. That is it. That's what the derivative is. If that limit exists, right? We found that sometimes the limit doesn't exist. All right. What else was in Cal 1? Related rates. You remember that because you enjoyed it so much, didn't you? Related rates. What was a related rate problem? Something like what? Like the word problems, right?
Like if you have a freaking like lighthouse.
Yeah. I can see your love and passion for that. It's the veins in your forehead are coming out. No, it's okay. So I'm going to probably star this one. This is probably the toughest section, one of the toughest sections in Cal 1, right? The boat problems, right? I mean, there's all these problems where you have something connected to the other. The unfortunate thing is those are the most realistic and useful problems because as engineers or people moving on to do things with math, that's the whole point, is to be able to take the real world and turn it into a math problem that you can solve. So being able to take the derivative of x squared plus 3 doesn't mean a whole lot. It's this sort of thing. But it's a struggle, and that's why in Cal 1 you see it for the first time. You get your first exposure to it. I don't think there's anybody in here with that would claim that they're an expert at that yet. So what else? Okay, that was usually that's towards the end, the antiderivatives. Optimization. Yeah, that was worse. So people have different opinions of these things. Optimization would be, what's like the classical example of optimization? Farmer and the farmer in the fence, right? Farmer in the. How many of you did a farmer and fence problem? Yeah. Okay. But there's lots of different optimization. These two are usually the main goals of a Cal 1 class. You want a student to be able to be okay, not like okay with any related rate problem, but to feel somewhat comfortable with the related rate and optimization. Now, how many of you spent a lot of time on curve sketching? Yes. Yep. I personally am not a big fan of curve sketching. I do it because we're supposed to. But at the end of the day, a computer is going to be better at sketching a curve than any of us will ever be, and it'll do it in a lot less time, right? But we should still understand the ideas of how a curve is created from the derivatives. You know, if I say that, let's say my feeling towards, what's something that's controversial? Okay, what happened on the VMAs? I never saw it, but what happened? It's been all over the news. What's her name? Miley Cyrus, right? My feelings towards Miley Cyrus, if you were to look at that as a function, it would have a negative derivative. So what would that mean to you? Where's that function? What's it doing? If I tell you a function has a negative derivative all the time, it's decreasing, right? It's going down. So, I mean, I'm just talking stupid math and real world. But the idea that the derivative tells you if your function is going up or down, and the second derivative tells you if you're concave down or concave up, right? Inflection points. That stuff is important. As far as all the mechanical sketching stuff, What else? Anything else? Implicit differentiation, correct. That's part of the derivative, but we had implicit differentiation. Now, L'Hopital's rule. Newton's method. Now, Newton's method is one of those things that a lot of us look at as being optional. And I did cover it, but not in depth at all. Optional. Only because Newton's method just shows you how a computer finds roots to equations. And so it's just like, here's the steps, and then you program it into a computer, and your computer does it, and that's it. So that's good enough, I think. But geometrically speaking, I think the heart of Cal 1 was you had a graph of a function, right? You pick some point on that graph, and you talk about the slope of the line that is tangent to that graph, right? I mean, that's like the main picture of Cal 1. And you can do that for, When you talked about optimization, right? Farmer, you were trying to find the highest point on the graph or the lowest point on the graph, but all of that was connected to that tangent line. So that's the picture of Cal 1. Now let's talk about what Cal 2 is going to be for us. Oops, sorry. I should follow my own rules and put my stuff away. So Cal 2. Cal 2, we're going to start out with a function again. And some of you probably already saw a little bit of this in Cal 1. And instead of looking at the slope of the tangent line, we're going to imagine dropping perpendicular straight down like this. And we're going to ask ourselves, what's the area inside, underneath that curve? What is it? And it's kind of like, well, why? Who cares? We'll see why that matters later. But think about what you're doing. You're trying to find the area of a figure that is not, it's not a circle, it's not a rectangle, it's not a square, it's just some arbitrary shape. So how do you find areas of things like that, right? It's kind of strange. Then we'll do something like taking that, and instead of having a function and finding the area underneath it, we'll have two functions, and we'll find, let's say, where they intersect like this, and we'll just try and find the area in between them, which is pretty much the same as the first problem, just a little bit of work we have to do to get to that. And then we'll go even further. We'll say, how about if you have a function and you have another function like this, and instead of having the area between those, take the whole graph, the two-dimensional graph, off the page, bring it out into three-dimensional space, and just rotate it around the x-axis. And if you do that, what would you get? So rotate around the x-axis here. You would get some weird-looking three-dimensional solid shape thing, right? It would be like, I'm not going to attempt to draw it, but it would be three-dimensional, wouldn't it? I could go in there and I'd stick my arm through that, and that shape, that three-dimensional solid, would have a volume to it, wouldn't it? And we'd be asked, what is that volume? So instead of area, we wrap it, make something, and it has volume to it. Yes? And then we'll go on to instead of wrap it around the x-axis, we'll say, well, why not wrap it around the y-axis instead? If I wrap it around the y-axis, do I get the same shape? It's not the same, right? It's different, and it'll have a different volume. So we'd ask ourselves, what's the volume of that? See the difference? Okay, and we'll extend and go beyond that. Another thing we'll do is we'll take a function like this, and we'll imagine just taking it, pulling it off the sheet of paper, pulling it tight like a string, and measuring how long it is. Now that seems like it would be easy, but it actually is pretty tough. This is called arc length. Okay, what's the arc length of that? And that's pretty useful if you have something that's traveling along a path, right, that's nonlinear, it's just moving around, and you want to know that the total length of that path, then you'd need to be able to get the arc length. And in Cal 3, you extend that out into three-dimensional space. So you're no longer like something on a flat sheet of paper, you're something flying around in 3D, and then you can measure how long that path was. But that's Cal 3, and that's beyond the scope of even this class. Back when I rotated this guy, look at this one right here. I said we would find the volume. We could also find the surface area, which would mean if we were to try to paint it, how much area would that be? So we could ask that question also. Now, all of these things that we do here are going to involve what's called the antiderivative. And I'm sure most of you saw some of the antiderivative. But there's other things you can do that I won't get into a lot in this class because we don't have time. Things like, let's say we have, these are called applications. Let's say we have a cube, okay, three-dimensional cube. Where is the center of mass of that cube? Where is its center of mass? It's in the center of the cube, right? Right in the middle. If I go in the middle of each of the sides, go straight in, straight down, right? Go straight in. Oops, way off there. That's the center, right? So in physics, when you have an object, you don't look at like a car when you're in physics as a car. You look at it as a point, right? Because every object that has mass has a center of mass. And so you can look at that object as being just a single point at its center of mass. But what if you have some weird shape like this mouse? Where is its center of mass? Well, doing antiderivatives and integration where we're headed allows you to find centers of mass of very odd-shaped objects. Okay? And not only odd-shaped objects, objects that are non-homogeneous. What do I mean by non-homogeneous? Yeah, I mean the density changes within the object. This one's not a good example, but trying to think of one right off. What changes density within it? That would. Yeah, but the soda is all uniform, right? I mean, the soda has pretty much uniform density. Yeah. Yeah. I'm trying to think of something that everyone could associate with that its density changes within the object. Jawbreaker? I don't know. Yeah, each layer of candy is a little bit. Yeah, I mean, anything that you can think of that changes within the solid, it changes its composition, its density changes. Then that can get very complicated with center of mass. I mean, if I take, like, let's just say I take a sheet of paper. Okay, here's just a sheet of paper. And what if I say over here in the yellow, and then the green, and then the purple, and then the blue, and then the blue. Let's say the yellow, the page is very, very light. And as you move, light meaning not very thick. It's very thin piece of paper. But as you move to the right, the paper gets slightly thicker and thicker and thicker. So maybe at the very left, real thin sheet, but by the time you get to the right, it's more like a piece of construction paper. Okay, so maybe like Bible paper to construction paper. So it changes its density within. Then the center of mass would be different than if it was all the same. If it's all the same, we call it homogeneous. If it's not the same, it's called non-homogeneous. So with Calculus 2, you can find centroids of objects that are homogeneous or non-homogeneous, which is useful in physics. Then, after all this stuff, we get into this thing called sequences and series, and I'm just going to save that for when we get there. Well, maybe not. How many of you know a little bit about the function e to the x? You've seen it, right? Yeah, one of its major properties is that it is the only function that is its own derivative. Well, the only non-trivial function, right? If I take the derivative of that, it is itself. Okay? Now, there are two people who created calculus, okay, from nothing, because calculus wasn't always there, right? Two people created it. They didn't know each other, and they did it in different parts of the world. Anyone know who the fathers of calculus are? Newton and Leibniz. Okay, and they came together at some point, and it was like, wow, we both figured this out together, right? Or independently, and we both thought of the same thing. So there was a major difference between Newton and Leibniz. Don't recall. I'm going to go with that. I don't think it's right. The difference is that Newton had what were called power series, and we will study power series. All right, that's what chapter 8 is going to lead us up to. Leibniz did not come up with this idea. So there were problems that Newton could do that Leibniz couldn't do. Like Leibniz would be like, oh, no, can't do it, sorry. I've never really quite been able to figure out how to do that. Newton was like, well, with this idea of power series, I can do that problem very easily. So let me show you what a power series is, just so you can see it. E to the x, you probably didn't know this. E to the x is actually this function. Oh. 1 plus x squared over 2 plus x cubed over 3 times 2 plus x to the 4th over, 4 times 3 times 2 plus x to the 5th over 5 times 4 times 3 times 2 plus ... forever. Now there's a pattern there. What would the next one be? X to the 6th over 6 times 5 times 4 times 3 times 2, right? So this is what we call a series. A series, you think of series just like one thing after another, right? It's a series of terms, and they are all powers of x, aren't they? Every one of those has an x to a power. This is a power series. Newton was able to discover that almost every function that's out there, you can find a power series representation for it. So let me show you how this works. If I ask you right now to get on your calculator and do e to the first power, what is your calculator going to tell you? 2.718, blah, 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 right? Well, all your calculator is doing when it does e to the first power is 1 plus, and it's replacing the x here. It's replacing the x with what? With 1. Okay? That's all it's doing. So it's going here and it's doing 1 plus 1 squared is 1 over 2 plus 1 cubed is 1 over what? 6 plus 1 over 24, right? You follow? Plus. Now, if you get on your calculator now, and don't do e to the first power, but if you were to do 1 plus 2 plus 1 half plus 1 sixth plus 1 24th and hit enter, you would be getting pretty close to 2.718. The further you go out, the closer you get to what e is. And what happens is your calculator goes out maybe 100 of these and stops and then returns the answer. Kind of follow? Okay, so Newton was able to say, hey, look, that's what E is. That's really what E is right there. And Leibniz is like, what the hell? Okay, whatever. Check it out, though. This is what I think is really fascinating about this. What is the derivative of this? Okay, what's the derivative of 1? 0. What's the derivative of x? 1. What's the derivative of x squared over 2? So the 2 comes out but cancels with the 2, right? So you get x plus, what's x cubed over 3 times 2? So the 3 comes out, so you have x squared, but it cancels with the 3 on the bottom, so you get just the 2. Do the next one. 4 comes out, right? But it cancels with the 4 on the bottom, so you get 3 times 2. What is the next one? 5 comes out, cancels. Do y'all see that? And what is it? It's the same thing, right? The 0 in front, imagine that 0's not there. Then isn't 1 plus x squared over 2 plus x cubed over 3 times 2 plus x, and it goes forever. That is what it started as. I like that. I like that a lot. That's the only function that does that. There's no other one you can come up with. So we will study power series, but it will first take us talking about what are called sequences, then we talk about series, then we talk about convergence of series, then we finally get to power series. All right, I think all that's good enough for us to start. Now we're official. Here's the way I try and do this. I'm going to try and do. So the way I'll write it, 5-1 means we're chapter 5, section 1 out of the book. 5-1-1 means chapter 5, section 1, first note. Okay? So this last number here is what note Ooh, that didn't work very good. That last one is like what note this is. So this is the first note of that section of that chapter. And then we get to 5-2, I'll go 5-2-1, and then 5-2-2, then 5-2-3. The reason I do that is just so if you ever are studying with other people, library, wherever, it's easy to cross-reference and talk about, hey, just look at what he did in 5.2.7. That's where you need to look. Okay, so it makes it a little easier to organize your stuff. Now, I know some of you watched the video from my old class because I can keep track of who watches the videos. So I know some of you probably are going to be a little bit ahead of everyone else on this, and that's okay. I'm prepared for that. So the heart of where we're going to start in Cal 2 is kind of like in Cal 1 we had the tangent line was the big problem, the big issue. Let's try and find the slope of the tangent line. Here we're going to start with the area. Yes? I'll tell you. Yep. The area problem. So what is the area of a circle? That's where we're going to start this. This right here is actually a capital S with a little line. That stands for the word suppose. That's a real mathematical symbol, okay? You probably won't ever see it in the book that you're using, but in higher math, we substitute that for suppose. While we're talking about it, anyone know what 3 dots is? Therefore, okay? And I'm not asking you to be an expert on symbols, okay? I'm just telling you. You may see me do that. If you ever see me use something and you're not sure what it was, just ask. So I'm saying, look, what's the area of a circle? Let's try and figure out what the area of a circle is, acting like we weren't raised with the formula. Because we all know the area of a circle is pi r squared, right? Right? Okay. Or we could Google it. So that let's act like we don't know that. So back in the day when humans were first, thinking and starting to get more and more advanced, and we were trying to figure out the area of a circle, how could they do it? So I'm asking you for some ideas. Let's act like you don't have pi r squared. How would you try and figure out the area of the circle? And let's act like we do know that the radius of this circle is 1. So how would you draw a circle? Put a stake in the ground, get a string, walk around, draw a circle, right? What's the area of that? Think of it in terms of like back in the day when humans, we're not going to get into like this debate about, the evolution of people. But if you believe that at some point we understood that we could feed ourselves off the land instead of chasing animals around, then we then started to fight over the land, right? Like, get the hell out of here. This is my stuff. That's yours. You stay there. I stay here. So we had to start to put borders on our stuff, right? So then it became, okay, you're going to have to pay for that stuff. How much stuff is that? Well, we had to measure it, right? So how do you measure something? Rectangles are easy, right? We just do length times width. But how do you measure something that's non-rectangular, like a circle? So how do you think they approached it? Break it into small? Like how? Squares and rectangles? Right? We don't know what that is as a circle, but we do know some stuff about squares. So one approach might be to go out there, you're saying like draw a square in there? Okay, so then maybe another, you're saying real small squares. This is fine. Each one of those I should be able to get a decent measurement on, right? Do you agree? Just imagine some poor guy out there measuring out a bunch of rectangles inside of a circular field, And then he could finally, get like approximately, right? Every little gap he could try and fill in. Now, eventually, his measurement tool wouldn't be accurate enough, right? And he would have to stop. Now, this estimate would be, if he added up all those rectangles, that would be too much, not enough. It'd be too small, wouldn't it? It'd be too small. So if I take all those red rectangles and add them up, that area, right, related to the true area, so this is the true area, the area of those rectangles there would be not enough, right? The area of the rectangles there in red is less than the true area. Agreed? All right, so then something else you might do, is I'm going to draw another circle here. Instead of doing a bunch of rectangles inside, why don't you do a square on the outside? Now that square is too much, isn't it? The area of that square is too much. But then I could start doing what? Subtracting rectangles from that, right? Measure out all these little rectangles in here and start subtracting. Now that area would be what? Greater than the true area, wouldn't it? So what I would have is back up here, I'm going to erase my little therefore. This is less than the area of the rectangles here in blue, right? What I know then is that the true area is smashed somewhere between there. And the better I get at measuring, the closer I get to the true area, right? This is what the Chinese did. And they came up with a really good approximation for the area. They were able to actually come up with something close to pi. It wasn't pi, but it was pretty darn close using this. This is called the method of exhaustion. You see why it would be called that? You would exhaust yourself doing all these measurements, hundreds of thousands. And that's what the Chinese did. They did that to get as accurate as they could. With me? Okay. Now, I'm going to show you, that was in a video I already showed. Okay, like if you watched the one, I'm going to approach this class today different than I did in my video because I want you to have some variety. First, though, how many of you saw this formula in calculus or in pre-cal? Area of a triangle. AB, 1/2 AB sine theta. Show of hands, no? Base times height? Yeah, most of us have seen this formula for a triangle. If you have a base and you have a height, then the area is 1/2 base times height, right? Yes? Now, this formula down here, can you all see the bottom of the screen? Anyone not see it? We're okay? This formula down here and this one up here are completely different. This one, in order to have the area, you need what? The height and the base, right? This formula here, you need the base, which I've got, B, right? But not height. What do you need? The angle between these two sides, right? I want to show you something. I think this is pretty cool. Go back up to the green one on top. I'm going to label this theta, and I'm going to call this side A. Can somebody tell me what sine of theta is? Look at this triangle right here. What's sine of theta? Sine of theta is opposite over hypotenuse, which is A, isn't it? Solve that for H. In other words, multiply both sides by A, and what do you get? A sine theta is H. Now go back to this formula, the green one here, and replace H with A sine theta, and what do you get? Oh, I can't. You get this, don't you? What's the difference? What's the give and the take between the formulas? The give and the take. Like in the top one, what do you need to know? Just the height and the base, right? You don't have to know anything about any angles, right? But you have to know the height, and a lot of times the height's hard to get. So on this one, the advantage is what? On the bottom one, you don't need the height, just two sides. But you also need what? The angle between them, don't you? So depending on the problem, sometimes it's better to use this formula, sometimes better to use this. Do you all see how these are the same formulas, just written out a little different? Okay. Everyone in here needs to be aware of this formula. It should have come up in Cal 1. Well, it's not always, but there it is. Now, I'm about to use that. Now, a lot of times in this class, I'll bring up what are called, everyone knows Wolfram Alpha, right? Oh, yeah, everyone loves Wolfram Alpha. Okay, Wolfram Alpha has a brain, right? When you go to that website, it has a brain that does all the computations. That brain is actually this program called Mathematica, which I own, and you can get student copies of too. But this is stuff that I put together, that I code up in C++. So if anyone's thinking of what is it, electrical engineering or no, computer science, sorry, and you like to code or you're getting into coding, if you're interested in any of this, I have no problem sharing my code with you. Or if you even go buy this program and you want to learn how to code, I'll help you. You just have to come in on my office hours. So what I'm going to do now is I'm going to show you my example that I made up using file not what? Let me try it again. Doesn't want to open it. Files. Well, I'm not opening anything if I can't. The file's not there. So just give me a moment here. Weird. Okay, so you, computer science people, this is the code, okay? Just so you see it. I'm not expecting you to understand any of it. This is the code that I made to create this in Mathematica. So here's a circle, right? And we want to come up with the area for this circle. An approximation. The Chinese did rectangles, right? I'm going to do something a little different. I'm going to do triangles. So what I'm going to do is I'm going to come up with, that's a right triangle, isn't it? Now, the side here, this length right here is 1. Okay, let's imagine this is a unit circle. Everyone okay with this? Now, if I go and do 4 of those, that would be an approximation, wouldn't it? Now, I think I need to write this on the board so we have it. What is the area of a circle with radius 1? What is the area? Pi r squared? But if the radius is 1, then the area would be what? Pi, right? If I do the 4 rectangles, the 4 triangles like I did here, the computer computed the area for me, and I'm at 2. The true area is pi. Pi is what? Approximately 3.14. So I'm pretty far off, right? I'm really far off. But if I add more triangles, I get a better estimate, don't I? So why don't I make these triangles a little bit smaller, like that. So now I'm doing 4 triangles in each quadrant. Now when I add these up, .06. Better, right? Better. But look at, I can still see that in there, can't I? Look at that error. I'm zooming in so you can see the yellow. I still have that error, right? On every one of those triangles, that little arc I'm missing. So how do I get better? How do I get a better one? Keep going, right? More triangles. So let me get my size of my triangles. I'm going to go with something ridiculous here. Now, Mathematica is slowing down a little bit because it's really having to think. It's doing a lot of computations right now. Look at that. I have 188 triangles all the way around. 3.141. Not bad, right? How could we get the true area, though? We keep going. It's not going to ever be the area, right? We're always going to have error. Unless you can let it go to infinity, right? Unless you have an infinite number of triangles. Right? And the idea of going to infinity came from the limit. Well, it's not because we don't know what it is and we keep approximating it. That's not necessarily it. We have a way to compute it, but the way we compute it, you have to get 1 decimal at a time, and you can never stop because it never repeats. I don't know who asked that. Okay, that's what I thought. So it's not that we're approximating it with triangles necessarily. It's just that in order to compute it, you have to keep going out. You remember I did that series where it had the 1 plus x? It's kind of like that. You would have to, the more decimals you want, the further you have to go. Okay. So this idea that we could get the true area if we could let the number of these things go to infinity is the heart of what Cal 2 is going to start with, okay? And the limit is what allows us to go to infinity, right? We learned that in Cal 1, like let x go to infinity. The idea, let it get bigger forever. Here, let the number of triangles go to infinity. That idea shouldn't scare us anymore. We know we can do it. We know we can get answers from it, right? All right. Was there anything else I wanted to show you on this? I don't think so. All right, next thing. Yes. Uh-huh. I don't know. 20 minutes? I mean, but I've been doing code in that program since I was in school. Like, I think I have a T-shirt. It's all torn up. It's like Mathematica 3. And we're there at 8 now. So Mathematica used to not have all this where you could slide things and change things. That's within the last 2 years. Yeah. What's that? They call it the manipulator. The manipulate. That function didn't exist. By the way, if you want any of these demos that I just, like the one I just showed you with the circle, if you want that without buying the program, you can get what's called the CDF player. It's a free player that you download from Mathematica's website. And then you ask me for the file, I'll email it to you. And then you can open it and you can be at home and you can actually mess with it. You can't edit the code, but you can get in there and mess with things. If you're interested. All right, next thing. So now we're in the second, no, so geometrically, how is it, what the heck? Oh, at the top here. Can we shut that door all the way, please? Thank you. Now we're going to change this up a little bit. We're going to step away from the circle for a second. And we're going to talk about a person walking. So take a second to jot that down. Given, wait, are we done in 20 minutes? Is that right? Holy crap. I yapped too much earlier. Given a person walks at 2 miles per hour for 3 hours, how far do they go? 6 miles, right? The time is 2 hours. The time is 3 hours. Their speed is 2 miles per hour. Let's graph this, though. Okay, let's graph this situation. So pay attention to the fact that we have speed on our y-axis and we have time on our x-axis. So on the x-axis, I'm going to mark off how much? On the x-axis. 3, right? Time, 1, 2, 3. So there's 3. And what was the speed of the walker? 2 miles per hour. So I'll just mark off 1, 2. And that speed never changed, did it? It was 2 the whole time? So if I just draw a line straight across like this, that would represent the speed. Now, what was your answer again? 6 miles was the answer, and everyone agreed with that, right? But I'd like for you to tell me how that's connected to this graph. Blocks? How about one big block? If we look at this as being one big block right here, then wouldn't you say that everything underneath this curve, the area of that rectangle, is the distance? Yes? Isn't it? I mean, this side's 2, this side's 3. 2 times 3 is 6. You think that's a coincidence, or you think that that is the way it always will be? It's always that way. Okay? Now, this is a very boring example because the person's just walking at a constant speed. So this is equal to the area down there. So geometrically, how is the answer related to our graph? I already said it's the area under the curve. Or under the curve's fine. It's not a curved straight line, but we can still call a straight line a curve. That all right? Okay, we're going to look at something a little more interesting now. Okay, I'll give you a second to jot this one down. How far does this person go in 5 hours? Now, what you have to keep in mind as you sit there in these classes is that, remember, you're going to have not only access to these videos, but you're also going to have access to these notes that I'm writing. So a lot of times that when I write things, I'll be going kind of quick because I expect that you'll have access to it, right? So who wants to help out here? What do we need to do? Okay, so you're going to approach it by trying to find the area underneath a curve. Okay, I like that idea. Between 5, you want to go straight up like this. Okay, where else? And 2. From 2, we'll go straight up like this. And we want the area of that. It's not a rectangle, right? But it's a geometric shape that I'm sure there's a formula for, right? Yeah, or you could look at it just being like a triangle and a rectangle or something like that. I mean, that's probably the easiest. So let's do this. Why don't we split this one up? So we have a triangle there and we have a rectangle here, don't we? And if we can find the areas of those, we'll be in business. So what's the area of the rectangle? I'm going to write it over here on the side. What's the area with the little subscript r? 3? Yeah, because the width of it is, what, 3? And the height of it is 1, and you can get that from over here, right? Because of the way I drew the graph? Okay, so the area of that is 3. Okay, what about the area of the triangle? Is 1/2 base times height, which the base is what? 3 again? And the height is 2. Yeah. Everyone see that? Any questions? So what's the total area? 6? Yeah, I haven't put it yet. That's the area. But in the context of the problem, how far does the person go? It'd be 6 miles. Now, what I did not give you in this problem is how fast this person was going, right? I just drew a picture of how fast they were going. So what happens if you look at this picture, right? This is the person's speed. When they start out, they're going really slow. And as time progresses, they actually go faster. So like they're picking up speed as they go. With this particular person, between 2 and 5 hours, they go 6 miles. Any questions on that? On where I got any of those numbers or anything? Okay. Next one. If this were Calculus 2, it would be too easy, right? If this was Cal 2. So how about this? Oh. I'm going to give you a second to look at that. What is the problem here? I want to know how far this person goes in 3 hours. Yeah, the x-axis is time. The y-axis here is speed. So same thing we've had before, time and speed. What do you see as being a challenge for us? Well, I should have said in the first 3 hours. Let's just assume that's the first 3 hours, right? So you would still maybe start out by going, at 3, you would draw straight up. And then at 0, aren't you just here? So you're trying to find the area underneath this curve, right? And I heard it. What's the problem with that? It's a curve, right? In the previous problem, we were able to do it because it was a triangle and a rectangle. The one before that, it was a rectangle. It was easy, right? How do you do this? Yeah, you could try approximating it, right? You could be like, okay, let me get a triangle. It's kind of close, but you're going to have error no matter what, aren't you? You're going to have error. So one approach would be to try and approximate it with rectangles, kind of like we did with the circle. We did a bunch of triangles. That's going to be the approach here. But this is where the Calculus 2 starts, really. Because if it's the previous two problems, you can do it easily. Well, with relative ease. This one, not so much. So right now, this is a big question mark, okay? How do we find that area? Don't know. How do you... Oh, I see what you're saying. Are you saying rotate it and then bring it on this side? I don't know if you're saying it. And then make a rectangle? I don't... Well, when we rotate, though, it becomes three-dimensional, so we get a solid now. We're still going to struggle with that. Let's hold off on it for just a second, because this is what I'm leading you into where we have to go from this. I forgot to... So here's where we start our idea of approximations using rectangles. Let's say we have a curve, any curve, and we're trying to find the area underneath it. Then what I could do is I could draw a bunch of rectangles in here, like this. And I could find the area of each of those rectangles and add them up, right? But all that yellow would be what? Error. E-R-R-O-R. Error, right? It would either be a little bit more than I need, or if it became under the graph, it'd be less, not enough, right? So each rectangle itself, like if I call this first one rectangle 1, rectangle 2, rectangle 3, rectangle 4, rectangle 5, each rectangle is either going to be too much or not enough. Too much or not enough, right? Now what I'm doing when I'm getting this rectangle is I'm picking the point on the right. So I'm coming out on the x-axis right there, that black point. I'm coming up to my function, and that's the height I'm using. Do you see that? I'm using the right endpoint. I'm going up to the function, coming back to the left. So I come up from this point, I go up to the function, and then I come back to the right. This point, I come up, and this one brought me a little bit under. Do y'all see that? That's right endpoint. You don't have to use right endpoint. You could use left. And you can use any point in between, which I'm about to show you. But does everyone agree that the more rectangles, what I have written here, the more rectangles we have, the better your approximation is going to be? Yes? Okay. We need to add up many rectangles. That's our task. We have to be able to find a way to systematically add up 10 rectangles, 100, 1,000, 1,000,000, infinitely many. So let me show you with the computer how this could be done. Just FYI, if you ever see me bring up an example like this and it has this down here, that means I've taken someone else's code that they've already done all the work for me and adapted it. So I went in there and I took their code and changed certain things to make it fit what I wanted to do. Okay, because I don't want to take credit for this if it's not mine. So what this little example does is it allows you to pick the function first. And then once you pick the function, you can do some things. So I'm going to pick the x cubed function. That's what x cubed looks like, right? Okay. Why did I go from 1? I want to change it to 0. Give me a quick second here. I don't know why that took so long. That's weird. There we go. Okay, so that's from 0. That's from 0 to 5. Okay, so in our problem, we went from 0 to 3, right? We're going to go from 0 to 5 just for this example. Right now, I have one rectangle. And it's the one that I go all the way to the end. I go up and I measure over. And I've got this big gray area, right? Now, what the computer has here, I hope everyone can see this. The computer has the estimated area. So that 125 is the gray, okay? The 41.667 is the real area. And we're not going to talk about where that came from, okay? But that's the real area under there right now. So one rectangle sucks, doesn't it? I mean, that's just a terrible, terrible approximation. So now what I'll do is I'll go 2 rectangles. Now look at the area. 78, that's better, right? 3, 4, 5, 6, 7, 8, 9, 10. And look at us. We're marching closer and closer and closer and closer and closer and closer, right? Towards the true area. But it's taking me quite some time to get there, right? More rectangles, better. That's what I want you to walk away from. Walk away from this with. The more rectangles we can get in there, the better the approximation is going to be. Everyone agree? Okay, now let me bring this back. Let's look at it, taking it off the left side instead. So now what I've done, instead of going out to 5 and going up and over, I've gone to the left side, up and over. But at the left it's 0, isn't it? So I don't have anything. So the area is 0. If I do 2 rectangles now, so this one is on the left side, I went up and over, but it's 0. Here I went to the middle, I went up and over. See that? Let me do it again with 3 rectangles. I start at the left end, I go up and over, but see, since at the left it's 0, there's no rectangle here. Then I go up and over to the right, I get this. Now look at this area, it's not enough, is it? But as I add more rectangles, I keep on getting closer to the true area. 37, 38, right? Now, I could also go to the middle. That means between 0 and 5, I pick the point right in the middle, I go up, and then draw a rectangle out. So there's the middle. Here's 2 rectangles. I went up in the middle and out to the left to right. Here I went up in the middle, out to left and right. Do y'all kind of see that? Turns out, though, doesn't matter. Although this one got there fast. Look at that. Look at that. By doing it in the middle, I got there really, really quick. For us, it's not going to matter. Because for us, we're not going to, at the end of the day, we're not going to count up 10 rectangles, 100. We're going to let there be an infinite number of rectangles. And so what this kind of demonstrates is it doesn't matter if you pick the right, the left, the middle, any point in between, no matter what, it will go to the true area. Yes? Okay. We are not going to have time for me to do the example that is going to make you, that that is going to be able to get you to do your homework properly. So I think for tonight, what I would recommend for next class, just take a deep breath and be ready to come back and do work. You're not going to have any homework assignment. That doesn't mean that I may not give you a quiz next class, because I may give you a quiz on anything that I said in here. Okay? Everyone, have a good day if I don't talk to you before.